Hello and welcome back to IzoMath. Today we're going to be talking about how we can use trigonometry to compute areas of various regions. So the first one we're going to talk about is a triangle today. Basically, here's an example that Professor Axler left us with, and it's find the area of a triangle that has the side lengths of 4 and 7 with an angle of 49 degrees between the two sides. And so we need to find the area of this triangle. Remember way back when earlier in the book and earlier in the videos that we know that the area of a triangle is 1/2 base times height. So for this triangle, let's first go ahead and label our points, the points that we have so far. So labeling what we have so far, we have this triangle. And remember, we also know that from previous sections that the area of a triangle is 1/2 base times height. Well, I consider this 7 to be the base. What I need to find out is this height. And that height, remember, is a perpendicular. I need to find that h value right in there. And if I break down this internal triangle right here, if I have a nice little triangle right there, if I break down that internal triangle, I'm able to solve, essentially find out this h, because if you can see that internal triangle, I have a right angle here, I have formed a right triangle. And essentially with this guy, if I use that small triangle, this 4 is now my hypotenuse. And we know from earlier, from our previous section, that we can find out, when given an angle, we can find out the other side, like using the sine function. So if I have sine of 49 degrees, sine of theta, this angle right here, that's equivalent to opposite over hypotenuse. Well, in this case, the opposite is the height of the big triangle, and its hypotenuse is 4. And using simplification, I can come up with 4 sine of 49 degrees is my h value. So given this value, I can actually find out that height. And so going through this, I now am left with subbing this value back into my area of the big triangle. Area of the big triangle, I can now have 1/2 my base, which is in the big triangle, is 7, times my height, and my height is nothing more than 4 sine of 49 degrees. And that will give me my area of the triangle. And obviously through manipulation and all that solving, that leaves me with 14 sine of 49 degrees. And that's going to come out roughly to being 10.566. So using the sine, I can find out the area of this entire region. So building on this concept, I know that this, if I had any general triangle, I can find out the height of that triangle by simply using my properties of sine, saying that h value is going to be nothing more than a times the sine of theta, that angle in between. So here, if I'm given a side, angle, side, or I know the two side lengths and the angle that's in between them, I'm able to isolate and find out what that h value is to get that height. And knowing that, that can help me put into, again, the formula of a regular triangle, or area of a triangle, is 1/2 base times height. Well, now that formula now becomes 1/2 base times my a sine of theta. So given any two side lengths with an angle in between of a triangle, you are able now to compute the area of that triangle using this formula. Here's an example from your book where it says find the value of b if a equals 3, theta equals 30, and the area of the triangle equals 5. So remember, up so far what we have is we know that the area formula of a triangle is 1/2 a times b times the sine of theta. So knowing that what I have here, I know this value is 3, I know the area is 5, and I know that this angle right here is 30 degrees. So I'm trying to find my b value. And my area, again, area in this case equals 5. So I'm going to go ahead and plug in the values that I have. I know the area is 5, and 1/2, and then the one side, a side, is 3, and the b is what I'm trying to find, and the sine of and then the sine of 30 degrees. So all my separate quantities here, that comes out to being obviously 5, 3/2, and then b sine of theta. Sine of 30 degrees we should know is 1/2, so we got 5 equals 3/2 times 1/2 times my b value, which comes out to being obviously 5 equals 3/4 b, and solving for b, going to multiply by, or divide by multiply by the reciprocal. So I got 5 times 4/3 equals b. So 20/3 carries the value of b. So that's how I go about solving that. Yes, you can use the other formula, the rewritten formula, which is simply the 2r over AB equals sine of theta. Either way, you're going to get the same answer, which is 20 over 3 for the value of B. One thing that Professor Axler points out in his book is the appearance of ambiguous angles. We just have seen that the area of the triangle is 1/2 one side length times the other side length and times the sine of the theta, or the angle in between those two side lengths. If I solve this for the angle, if I'm given the two side lengths in the area and I want to find out the angle, obviously I can solve sine of theta is going to be equivalent to 2 times the area over the two side multiplication of the two sides. But something interesting shows up on this, and here's an example of that. In the second example, in Axler's book, he talks about, suppose the triangle has an area with side lengths of 3 and 8, and then an area of 6, and you want to find out the angle in between the two sides. Well, drawing that triangle, I can draw a 3 and an 8 and go through and try to solve this. And obviously, using my formula, so to find the sine of theta, we know it's going to be twice the area, so 2 times 6 over the multiplication of the two side lengths, which is 3 times 8, which comes out to being obviously 1/2. So, given that the sine of theta equals 1/2, we know that the inverse of sine of 1/2, or the arc sine of 1/2, is equivalent to pi over 6. However, it's also equivalent to 5 pi over 6, and I can continue on, multiples of 2 pi, these guys all the way throughout. So the question is, and we know that pi over 6 is 30 degrees, and we know that 5 pi over 6 from previous sections is 150 degrees. So the question is, which one is our answer? Well, we can eliminate the ones that are greater than 5 pi over 6, because right here is 150 degrees. The next version of that is 300. The other possibility, I guess, is 390 degrees, and then also 510 degrees. But we know that these options cannot happen because the total degrees of a triangle is 180. So it has to be one of these two. So let's find out which one it is. And interesting enough, given that we found out the possibility is either 30 degrees or 150 degrees, and we eliminate all other possibilities because they're greater than 180, here is a triangle that has the side length of 3, 8, with an area of 6, and it has that angle in between to be 30 degrees. While this guy also has a side length of 8, another side length of 3, and his angle, believe it or not, is 150 degrees. And his area is also 6. So there's actually 2 possibilities. Then that gives up the ambiguous angle scenario. So there's 2 possible answers to this question. If you're not specified with more information in terms of whether the angle to be acute or obtuse, these 2 triangles satisfy that possibility. So you want to be careful when you're working through these examples. Now for a parallelogram, the procedure for finding the area is very similar to what we just did with a triangle. Given the fact that you have an angle and the 2 adjacent sides lengths, you can find out the area of this parallelogram using what we just did. So again, we need to find out the height, and of course we know that the height of this guy is, again, my height of that side is going to be a times sine of theta. And from here, we can find out that we remember that the area of a parallelogram is basically base times height. And in this case, the base is going to be b, but the height is now going to be a sine of theta, or more appropriately, ab sine of theta is going to be my area of a parallelogram. So we use this concept that we just built on. And if we're given other polygons, I can also use this procedure to find out the area of all polygons. Simply by if I make cut every polygon into separate individual triangles, I can use this concept to come up with, if I can make triangles within that regular polygon, I can divide them up and I can find out the area of each individual triangle and then multiply by how many triangles I have, and that's going to give me the area of the polygon. Hope this helps, and we look forward to seeing you on the next edition of ISO Math.